Hello, everyone, and welcome to today's Smart Manufacturing webinar, Advanced Root Cause Analysis and Diagnostics from Wafer to Final Product. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You have joined listening with computer audio, but you can go ahead and switch over to phone call if needed. The dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send them in at any time. We'll collect these and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded. You'll receive a follow-up email within 24 to 48 hours with a link to view the recording. Now with that, I'd like to introduce the presenter for today's webinar, Dave Huntley. All right, he's also the product manager for assembly products at PDF Solutions. Go ahead and take it away.
Okay, next slide, please. Jessica, I don't see the next slide. Oh, okay, and the next. Let's go to the speaker side. Yeah, so, well, welcome to the webinar. Yes, as Jessica said, I'm Dave Huntley, product manager at PDF Solutions, and we also have with us Zoe Conroy, senior hardware engineer manager at Cisco, and Warren Savage, who's a visiting researcher from the University of Maryland. Unfortunately, Zoe's webcam doesn't seem to be working, so which is a pity, because you'll have to now put up with Warren and I's ugly mugs for the rest of this. So, next slide, please. So, I'd like to start, first of all, by defining what we mean by traceability, because some of you are probably familiar with just programming an identifier into the device at wafer sort, at wafer test, and then reading that identifier out later on. And that is your traceability that you're familiar with. But we're not talking about that sort of traceability. We're talking about traceability which includes all the active and passive components and all the raw materials and all the process steps that go in to make the entire final product as it goes into the field. In particular, the assembly steps that take place after wafer sort. So with that in mind, when I say traceability, that's what I mean. So this talk today, we're going to start off by going over some real-life use cases which illustrate the problem that we're trying to solve. And those problems come into the category of fast and accurate response to an RMA, predicting and preventing field failures so we don't get RMAs in the future. How can we match die in a multi-chip package based on the matching wafer sort parameters, wafer test parameters? How can we ramp up a new product introduction yield ramp for a product which involves advanced packaging? This is a challenge. And finally, talk a little bit how can we prevent counterfeits and security breaches in our supply chain. So then, having gone over that, I'm going to try to summarize what you need to put in place to solve these problems, and then give a brief demonstration of the Exensio product, which is one of those solutions. Then we'll move on to the guest speakers, Zoe and Warren after that. And hopefully we'll have enough time left for some Q&A when we get to the end, assuming I stay on time, which I'll attempt to do. Can I have the next slide, please? So we'll start off with this problem of providing fast and accurate RMA response. We'll look now at the automotive industry, which the graphic on the right shows quite clearly that the recalls are increasing year on year. And in 2016, for example, the total cost to the US industry was $22 billion. And of that, 1.32 billion was related directly to electronic failures in the form of claims and warranty accruals. So, a bit of a pricey thing, quite eye-watering numbers, really. It doesn't have to be that bad. The number of cars, when a recall occurs, typically, a huge number of cars get returned. So they're unable to completely identify which cars are actually affected by the root cause. So many more cars are returned than are really necessary. And of course, that damages the manufacturer's reputation significantly. If we were able to have in-field monitoring and upstream traceability, we would be able to much more rapidly identify and contain which vehicles are affected by this particular issue. And furthermore, when we finally get the actual root cause, we can get there quicker and with much more confidence that we found the real reason. And the savings on the recall cost, with just probably one incident of one of these recalls, you can get an instant ROI on whatever you invested in the necessary traceability. You get an ROI, in one event, I think. And then, most importantly, apart from the dollar impact, you get to retain your reputation as a manufacturer. That okay, things do go wrong, but I can fix them. I have a very fast and accurate response in place, ready to go, and therefore I'm better than the other guys. So next slide, please. So here's some more data on the automotive side of things from some data from BMW, which breaks down the costs of recalls. 22% is electronic and electric. Of those, we have a breakdown of active and passive, and then a breakdown of semiconductors. So 77% are from semiconductors. And of those, we have a breakdown of the failure mechanisms. I'd like to draw your attention to that 6% number at the bottom, which says retested without observed failures. That's not a big percentage, but on the other hand, it's a very scary thing because it means that we didn't learn anything from this failure and we have no opportunity to fix it in the future, so it will probably happen again. The next thing I'd like to bring your attention to is the 12% of assembly as the failure location. So this number is pretty small, actually. We have other numbers which suggest more like 35 or even 50% of failures typically in automotive are coming from assembly. But even so, whatever that number is, it's growing, and it's of a concern because the traceability in assembly is way below what it is in wafer fab, and therefore it's very hard to get inside there and find out what the root cause was and then therefore fix it. Next slide, please. So this is another case where we have a smartphone battery catching fire, which happened a number of years ago, and this was a pretty well-known case. But first of all, of course, it was scary having these things blowing up on planes. So they recalled them and they looked at it and they found that supply array had a design flaw, which we see on the right. So they said, okay, well, we'll fix that and continue shipping the product. But then, even just 2 months later, they found they were still exploding. So they found another defect from supplier B, and this was a manufacturing defect in this case. So, this was a hugely costly exercise. Manufacturer reports 5.3 billion in costs, and other people put it more like 17 billion. And the sad thing is, it's only a handful of phones were really affected, and only a handful really needed to be recalled. But instead, they were all recalled, and ultimately the product line was scrapped. So next slide, please. So this is, we're moving now from the response to an RMA to once we've responded to an RMA, how do we predict and prevent the failures occurring in the future? This comes down to this whole drive towards zero defects. It's easy to talk about zero defects and push toward it, but it's much less easy to achieve. One thing's for sure, we need to know every time anything happens, anything go bump in the night out there in the field, we need to learn from it. And this chart below shows that 32% in this case were no trouble found was the final conclusion of the recall, which means that for those recalls, we never learned anything and we never improved anything in terms of reliability, which is a significant problem. And that's probably because of the gaps in collecting data and traceability from the assembly and raw materials that took place after wafer sorts. Next slide, please. Sorry, it's catching up. Yeah, so this is I want you to consider an application, another situation where we're trying to match die in a multi-chip package. So imagine there's two die or 2 or more die that end up in a final package, and they have to be matched or calibrated to one another in order for the final application to work. Without this calibration, the device simply doesn't work and cannot be sold. So let's look at this flow and how this took place, how this thing is assembled. It's, first of all, the wafers are being manufactured from several different companies, Subcom 1, 2, and 3, and their yield was low, so they picked the devices from the source wafer and put them onto a reconditioned wafer, and they sent that reconditioned wafer on a frame to the assembly house, which assembled the devices onto a strip in a multi-chip package. Then the package was singulated, then another die was placed on it, and then there's a 2D code marked on the package. That 2D code was then read by the final tester, which was then able to use the traceability to go back all the way to the very source wafer, read the parametric test results it was interested in, and use those to calibrate the devices together. Now, notice that all of this doesn't depend in any way on ECID, so there's no identifier on any of these chips that you can read. And in fact, these chips can't even support ECID. There's nowhere on them to record an ECID inside them because there's MEMS devices and so forth in there. Okay, next slide, please. So let's move on to the problem of, let's say you're introducing a new product and you want to ramp the yield up, and your product contains quite a bit of advanced packaging. This is actually a very real problem developing now because of this trend that you've probably heard of combining various different, doing heterogeneous integration of IP at the packaging level rather than the silicon level. And TSMC have a program in this direction, and so does Google and AMD and Intel. So it's a mainstream trend. And the problem is that your yield problems are going to probably take place in those advanced package levels. And it's very without complete visibility of all the process variables and so on in there, it's going to be very, very hard to ramp that yield up. It's going to be like needle in a haystack trying to figure out how to fix it. And ECID would not help you in this because it only gives you visibility at the wafer sort level once, and then again another look at it at final test, but nothing in between. Okay, next slide, please. So here's an example of one of those advanced package, a well-known example of one of these advanced packaging devices, the iPhone 10 and iPhone 8, and there's various devices here from TSMC and Samsung and Hynix, Micron, etc. And it uses a lot of advanced packaging techniques in order to be able to compress the whole device into the slim form factor that we expect from a phone nowadays. So a lot of the problems that take place in the yield of such a device relate to assembly and not to the raw silicon and things that take place in wafer fab. Next slide, please. So here's one last problem, which is the problem of preventing counterfeits and ensuring security. So counterfeiting is a massive problem. We've got a figure here of $169 billion it costs the industry worldwide, and $75 billion of that is attributable to the semiconductor industry alone. Actually, I've seen numbers in the trillions, but I was conservative here. But whatever it is, whatever numbers you look at, they're eye-watering. And further than just simply cost, there is a concern of security. So the department, there's an estimated 15% of spare and replacement parts for the DoD equipment, which are counterfeit, according to anyway, that's reported by the DoD. And the World Health Organization reported that 8% of all medical devices in circulation are known to be false, which is known to be fake, rather, which is a big concern if you happen to be a recipient of one of these things, you're a patient and you have, say, a pacemaker in, and it's not a very warm, fuzzy feeling. So most of these counterfeit products enter the system through supply chain vulnerabilities, and manufacturers need to analyze their supply chain to identify the gaps where perpetrators can compromise their products. So Warren is going to talk more on this in his talk later on and talk about the attack vectors and so on. So I won't go any further onto it here. Keep ourselves on track on time. Next slide, please. Oh, I believe it's the poll. I believe you should be seeing a poll question popping up soon. Okay. So yeah, we're trying to assess. You know, we're saying we think this is an important subject, and we just want to know if you agree and whether you've had an experience with it yourself. Okay, so well, that's a pretty good chunk of people have had an issue in the last 3 months. So that's it seems that we're not just making this up. That's good to hear. And then of course there's not part of your job description, but okay. So overall there's definitely this you're having some effects. Okay, that's interesting. Thank you very much. So next slide, please. So we're now into the solution space. A perennial problem of men, apparently, but I think it's actually an important space to be in for everyone. So, yeah, so let me remind you the definition we had of traceability from the beginning, which says that it is fully inclusive of traceability with active and passive components, materials, and all the process steps, in particular assembly. So bearing that in mind, what do you have to do to get this traceability in place? Well, it comes down to the 3 C's. Connectivity, which you need to be able to connect to the equipment on the factory floor and collect highly granular data per device, such as FTC trace data. Feed that data into a big data and analytics engine and system to derive insights. And then you need the connectivity again to feed the control strategies which are derived from those insights back to the factory floor. So connectivity is a critical piece. Without it, you can't really achieve the results you need. The next one will be the coherent data model. This is absolutely critical. Fortunately, we have the SEMI E142 standard provides a common semantic data model which describes the materials and the die and the materials, the processes and the metrology and tests, etc. That covers the entire, is applicable to the entire supply chain, you know, to wafer, to packages, to printed circuit boards, etc. So this is an important foundation to the what you need to absorb and take on board. And finally, you need a cloud deployment, because you need to share data across the supply chain. First of all, it's big data, a lot of it, and you need to make it available to the analytics, the AI and machine learning algorithms, etc., to drive the insights required. So the big 3 C's. So next slide, please. So not only do we need to deploy the 3 C's, we need to do it across the entire supply chain and across the entire life cycle of the product. So that's from wafer design all the way through to, you know, wafer fab, test, assembly, package test, distribution, printed circuit board assembly, and even out into the field where we have phone home systems where you in-field telemetry, where the devices are reporting back even when they're in the field, like right to the end of life. This slide, by the way, is courtesy of the GSA TIES system, which is the Global Semiconductor Alliance Trusted IoT Ecosystem for Security. PDF is participating with GSA TIES, and GSA TIES is participating with a number of other players in the industry, and also with standards bodies such as SEMI, IPC, and ISO. I myself am the co-chair of a couple of task forces at SEMI, which is a Single Device Tracking Task Force and the Advanced Back-End Factory Integration Task Force. So anyway, so significant participation by PDF in the standards space in this area. Zoe will be going on to discuss the requirements to share the data that's up there in those blue databases at the top, where the trusted private data is in the data silos of each node in the supply chain. And there's a sort of, she'll be just discussing the requirement to accomplish something which meets the data exchange network we're showing there in blue. And Warren will be touching on the importance of having a trusted and secure and what's the word, immutable blockchain record of the chain of custody of devices through the supply chain as a way to track and prosecute counterfeits and security breaches in the DoD supply chain. And Warren's also working with me on the Single Device Tracking Task Force to define an industry standard so that the entire industry can benefit from the investment that DARPA and AISS program is making, that he's involved in. Next slide, please. Okay, so I keep talking about, you know, we've got to track without ECID. So how do we do it? So this is a very simple process. This diagram shows a very simple process which illustrates how the Exensio platform collects data and records it in E142 format. So let's go over it briefly, starting from the die attach. We are picking good die from a wafer based on a wafer map and placing them at good locations on a strip. And we are at the same time recording the XY transfer, and we are recording other materials such as the epoxy lot number that was used for every individual die. We go to the wire bond, we do the same. We bond only the good devices on the strip, the good locations on the strip, and we record, say, the gold wire lot, for example. Then it moves the devices, the package is molded, and then it goes to laser mark, where we mark a unique code on each device and relate it to the strip ID and XY. The strip is then singulated and placed, the package is placed in a tray, and the 2D code is read by final test, which completes the loop. Because the 2D code will then connect back to the strip ID and XY, and then all the way back to the wafer. So we're doing all of this basically by connecting to the factory floor in real time, and none of this depends on ECID. Even though this is a simple flow, it's also applicable to the more advanced assembly flows like fan-out wafer level packaging, and package on package, and all these other different technologies which are being promoted. It's also applicable to printed circuit board assembly. There's nothing special about either one. This E142 can handle the complexities of all of that. Next slide, please. I'm running a little. Okay, so I'm going to keep this fairly quick. With this is basically talking about the need to go end to end. We're talking about the value is being added at assembly, and so also the reliability errors issues are also coming in after the wafer sort area. So you need to collect data from all across the product life cycle and collect in a big data system and feed it into the manufacturing analytics. And so this is what the Exensio Analytics platform is capable of doing, and this is our vision for the future. Next slide, please. The key part of that future is that we need to be able to share data, as we've mentioned before, across the supply chain between you know, assembly and test and wafer fab and board assembly and so forth. But to do that, we need to have a secure and a high quality data exchange network, which allows bidirectional data exchange. And the Exensio platform includes a component called DEX, which is that's its mission in life, as shown here. And we also anticipate that DEX will interface to the blockchain chain of custody systems as they emerge. Okay, so with that, I think we'll go on to the demo. So let's see, show my screen. Okay, so here we have sorry, I've got to get a couple of windows off the top of this. Right. So here we have the dashboard, Exensio dashboard, and we're not going to show a great deal of the analytic capabilities of Exensio today, other than the traceability aspect. Although we will be touching on one fairly advanced module called the Equipment Trouble Prediction (ETP). Anyway, to do this demo, I thought I'd follow two different scenarios to basically illustrate the capabilities. The first scenario would be we've had an excursion in final test. So suddenly this bin 4 has poked up its ugly head, and we want to know why. So we selected it. We look down at the various tests below here. The final test, we're looking at the tests which are involved in this fail. We can look at the parameters, look at the distribution charts and the quantile plots. So this is basically Analytics 101 for final test data, but we don't see any signals there. We don't see anything obvious, which is explaining why this bin 4 is suddenly peaked up. So we're going to go back in time and go back into the assembly sites. Let's go and take a look at the strips where the package were assembled. So here we have, here we see a list of a gallery of all the strips which were used to assemble these particular packages, which had the final test fail. And we don't really see any spatial pattern here. Basically, they're evenly distributed more or less across the strip. The top left diagram is actually a stacked strip map, and any spatial pattern would show up there. So let's go back even further in time, go back to wafer sort, which is fundamentally is only made possible by the traceability. So this will give us a chance to take a look at any spatial patterns that might take place on the wafer. Well, I think the GoToWebinar is slowing this down quite a bit. It was a lot faster when I did this morning. Anyway, so now we see that those devices that failed the final test. Actually, before I go into that, let me talk about what we're actually looking at here. This package is made up of a large device on the base bottom from product A, wafers of product A, and then there's a smaller device from product B, which is placed on top of it. And then it has 3 smaller devices on top of that from product C. So we see below, we see a product A, we see an edge pattern here emerging. So that may well be the root cause of why this final test fail started to take place. We could go down and look at compare the final test parametric test results with the wafer test results. And here we have combinations of parametric tests from final test and wafer sort. And they're ordered by their R-squared values. So the first one we see here shows that there is a correlation. But the distribution of the devices which had the final test fail does not seem to show that they're outliers from this correlation. Anyway, you could go through a lot of analysis like this. Basically, there is no signal here. So the signal seems to be, in this case, that this final test fail was related to an edge effect on product A on the wafer. So moving back to, let's go to the next use case that I wanted to go through. There's an RMA case. So here's a case where you've received a bunch of parts back and they've given you an RMA report and they've got a list of package IDs. You come into this and you select the package IDs which are in the RMA, which are the ones shown in black on the left. And again, there's no clear signal coming from final test. So you go back to you take a look and see if there's some sort of a wafer pattern. So I'm now going to go back to I'm going to click on the strip to wafer sort. Which again is so it's a little slow. So we're going to try and look at it from the okay, so here we see the pattern of these devices on the RMA and how they're laid out on the wafers on product A, B, and C, and we don't see any significant straight spatial pattern. So then we can take a look at wafer sort correlation again, look on the parametric level. And again, these components are evenly distributed. They don't show any particular outlier pattern from this correlation. So let's take a look now at the equipment in assembly, the assembly equipment used. And bingo. Looks like we might have something here because all these packages were manufactured on wire bonder 105 and not the other 3 or 4 wire bonders shown here. So maybe there's a problem there. So we're going to drill down on this particular wire bonder. And now we're going to see what we're looking at here is we're collecting, there's about 100 sensors on this wire bonder. We're collecting traces from all of them, for every single bond, and a bond is the bond on the die and the bond on the package. And so you can see there's a number of different traces here. I can select a different one. But I'll focus on this number 4 because it's a fairly obvious pattern to it. All these trace data are being fed into machine learning algorithm, which is part of this equipment trouble protection module we have. And the machine learning algorithm is determining what is a normal trace and what is an anomaly. And it gives it an anomaly index. If the anomaly index is above 0.5, it shows up on this histogram on the left. And if it's above 1, it's considered to be a bit of a concern. So we're looking at number STID 04. And over here, this is the these are the individual bonds. So we can look at this one here is classified as a reference. So we see that green line. I don't know if this is showing up in time for you, but this is a normal trace in the middle, and this one down here, this one that I'm highlighting here is an anomaly. So the peak is a little bit earlier and a little bit higher, and the machine learning algorithms identify that. So that means that we can now relate these RMA failures to signatures on these traces. And once we've done that, we can use those signatures to find out what other devices need to be returned. And we can also put in place control strategies which control limits around these this anomaly index in order to prevent these parts from being shipped in the future. We can also feed this information to the scientists, which can look and find out why there is an anomaly in this particular sensor. And maybe they can fix the underlying root cause and get rid of it completely. So I'm 2 or 3 minutes over, so I better finish it there. So that's it for the demo from me. So I'd like to introduce Zoe from Cisco for the next part.
Hi, thanks, Dave. Just waiting for the slides. Here they are. Thanks, everybody. My name is Zoe Conroy. I'm a hardware engineering manager at Cisco for silicon DFT test and product engineering. Next slide, please. So let's look a little bit at exactly what we mean about various traceability definitions. So IPC have come up with this take on external and internal traceability, where external traceability is the flow of materials and devices between supply chain members as defined in the SEMI T23 standard, and potentially from the new emerging blockchain standard that's being worked on right now. Internal traceability is more within a factory and captures a relationship between the assets coming into, flowing through as the manufacturing assembly takes place, and then flowing out of the factory of the assets there. And some of these might follow the SEMI E142 standard that links a lot of the manufacturing data, metrology, and test data that is going on in the factory. So traceability overall is a combination of this internal and external traceability. And David mentioned at the beginning, it's not limited things like ECID or PUF, electronic chip ID, or PUF are these unique identifiers that silicon parts can have. I call them like smart parts, where you can actually program and read IDs out of these parts. It's really to any single component that is going on any product or any board, raw materials, passives, MEMS devices, and so on. And within this webinar, we're talking about all of these components and constituent parts. Next slide, please. So here, what are the top drivers to implement traceability? What's really driving the industry to do this? In my mind, it's really a faster, more sustainable yield lamp through the whole assembly and test process. So this is it really starts, at wafer, before wafer sort. You want to be identifying, the wafers that are coming through the fab, right through to dicing, chip test, any module level test, to any product board test, in-circuit test, board test, system test, and then final system ship out, and then even to the customer. You want to be able to really trace every single component and every test and assembly and shipping step from the beginning to the end over the whole life cycle. And you want to do this because you really want to see if anything is deviating from the norm and causing you a line stop or a yield loss or a product malfunction, we have the capability and the means today by logging all the appropriate data to really figure out super quickly what went wrong, where it went wrong, and ultimately you also want to figure out why it went wrong, and that means dumping pertinent data on fail or on any excursion so that you can fix it quickly. And now we have things like the cloud computing and data analytics tools. We really are in the place today that we're able to do this much quicker than in the past. So this goes on to the fast and accurate RMA response. If you do get a fail, even a fail in your manufacturing flow, board assembly, if you're a component supplier and you're shipping components to another supplier to do final board product assembly, and parts fail there a lot, parts failing in the field, and you have RMAs, you're able to really trace where that part, where it was shipped, who shipped it, and any parentage on that lot to find out potentially where an excursion occurred. Now we have things like telemetry, a lot more networking out at customers. You really want to be able to measure some sort of field performance too, not only when a product fails, but if a product potentially is going to fail some point in the future, if there's an excursion happening, and that's around predicting and preventing field fails. Next slide, please. So areas of traceability needed are here at the highest level. It starts at wafer and package. We have so much more die stacking going on today. You want to be able to identify everything on that die stack. A heterogeneous integration is many things assembled on an interposer, not just necessarily silicon, but MEMS, photonics, lasers, lenses, things like that, many different things. On a heterogeneous integration, you want to identify quickly if something is bad, why it's bad. It can save a lot of time and cost to be able to identify and fix quickly. Module level, this is a whole another area, things like photonic modules, highly complex, many diverse components on there, tiny little components that need expert assembly and test. Any one of those can have an excursion at any point in time, needs to be traced. Board level, so I'm talking more of a bigger board level, routers, switches, PCs, bigger components, system level integration, and out at the customer site. So really traceability is required at every single step from this end-to-end value chain. And I put it, new behaviors can transpire, and you need to be able to trace and debug throughout the life cycle. Just because you tested a wafer and said my die passed, we see so much in the industry these days that it's like the known good die syndrome of, yeah, it was fine at wafer sort, but as soon as I put it in my product and it started communicating with other dies from other suppliers on that board under a specific power, temperature, voltage condition, then I start to see a marginal die. So these new behaviors on parts can transpire any time in this product life cycle that you need to be on top of to find out immediately, is my behavior changing? How is it changing? And is it going to be an issue in the future? Next slide, please. So here, the point of this seminar is really traceability, but I like to put debugability in there too. It's fine being able to trace something, and you want to trace something because when it goes wrong or starts to go wrong, you want to know where and why and how. But then it's the how is the debugability. Just knowing that it went wrong, it failed, that's cool. Yeah, you replace it, but ultimately you need to know why did it fail, because are the components from that same lot going to fail too? Is it, if one lot fails my manufacturing, might the others fail out at the customer? I need to be able to fix it so it doesn't happen again. The failed parts is time and money wasted, isn't it? So all the while you want to trace this part. If it fails, then that's when you need to step up and take action. So if it fails, you want to know, why did it fail? Firstly, you trace exactly what failed. Why did it fail? You need to, on fail, you want to dump actionable data that will allow you to take some good action at the time of fail to start being able to fix it. And this is the key point here, is that doesn't just happen overnight. It takes a lot of expert engineering effort to say at any point in my product, if any part, any component fails, what signature am I going to dump out on that fail that allows me to not only trace the part, but to debug it, to debug to what failed and why it failed, how it failed, that when I send it back to my component supplier for retest and RMA, that they're going to be able to reproduce that fail immediately. So this whole dumping of actionable data is very, very key. And then after that comes data analytics to really correlate these fails, up and down the supply chain to why did it happen? Will it happen again? I need to correct it. But of course, with this data analytics comes a whole other issue of now you have tons and tons and tons of data flowing up and down your supply chain. And number one, what analytics do I need to do? When I have gigabytes and terabytes of data, how am I going to do it? It becomes a real burden trying to do these correlations in similar formats. And when I do it, is it going to be able to drive immediate action? These are big problems that we're seeing now in the supply chain. And then on top of that, once we're talking about field fails, you want to be able to predict if at some point a part might be starting to fail out at the customer site. Next slide, please. Did the slide move? There we go. So I have a few quick examples here. So for example, when you have something like a photonic module or co-packaged optics, there are many constituent parts that go in here. The thing about optics, and particularly photonics, it's all around the lowest cost of the module and the highest quality. These modules are in everybody's network. Internet, if you're downloading videos, you're on a video, everybody's going to be is already using photonic modules. And you know how frustrating it is when your network goes down. And it's all around the low cost, of these parts. So being able to test what failed when at any point, be it a lens, a laser, or a photonic part, you have to find out immediately when it failed and be logging all that data. And the next slide, please. Here is a much bigger level. So the system traceability here is a networking product. Components are easy, yes, things like memory parts, ASICs, network processors, microprocessors, they're all easy to trace because they usually have electronic IDs. But then there's many other parts that you can't trace like that. And certainly from the Cisco side, we have a specification here around what goes on a shipping label, what goes on each part, how that's traced and read, and the data, because obviously many fails are due to non-silicon parts for whatever reason, and those also have to be traced along with what board they went on and the time and the manufacturing place and all those other IDs that go with it. Next slide, please. And finally, field traceability. Now we have the capability with highly networking parts and IoT to be able to do this now. From the manufacturing side, every single product and all the bits in the product are already traceable to a product serial number. So that's already been done. So now you want to trace or monitor that piece of equipment, monitoring in the application area at the customer site. Not only technically, it's very feasible today to do that, but the harder part is really around all parties agreeing that there is a data transfer of what's going on at the customer site and how that data would be used. So clearly there's a big business area here for data security, honesty, and good reasons why we need to be running telemetry. Next slide, please. So on that point, security is a huge part of the whole traceability, and particularly when you now have data, like the external traceability data moving between parties, you must have it secure. Often there would be regulations between different customers, different countries, license agreements, expectations of trust and privacy. These are huge, above and beyond the technical side of it, which from usually as engineers, we say, oh, that's easy, we can move data, but then this whole security is a huge aspect. Access control, who gets access to it, how is that done, how do we prevent data leakage, and things like that are also a huge part of this business now, above and beyond the engineering effort. Then probably everything needs to be documented, licensed, signed off, agreed upon by various legal teams and compliance teams and security teams as well. Next slide, please. So the security and the data transitioning is a huge aspect of what we're doing today. But also on that note, we're using cloud a lot, cloud to do analytics, cloud to store data, many different types of data from many different test steps across the supply chain, the customer being uploaded, data formats, and the best data formats to enable fast analytics is I'm going to say is a huge problem right now. Data comes in all sorts of formats. Some are readable, some are full of garbage. You got to figure out what's useful and things like that. So it's an awful lot of work to get this done, and certainly doing the right analytics, I know right now is still very, very painful across different sites, different clouds, getting data transferred and secure and all that. It's really very manual job and not easy to do that. So we have a lot of questions here around best formats for data, best ways to transfer, what are the best tools to do this, which are the best tools for analytics and to do the business intelligence. What analytics are needed, yeah, that's really a custom thing depending on your product and your parts. So I have some examples here of, the common tools that are coming up, AWS and Web Services, Tableau and Extensio, as we're talking about today. There are many other common formats too, but there's still a wide range of formats out there, a lot of ad hoc formats, but most commonly we have E42, STDF, CSV, JSON, and Avro are common formats at the moment. Not sure where we'll be in 2 years' time with these types of formats. So that was all I had today. I'm going to hand it now over to Warren, who's going to talk about counterfeit.
Thanks, Zoe. Yeah, hello everyone. My name is Warren Savage. I'm a visiting researcher at Maryland, as Dave mentioned. Next slide, please. So I thought I'd tell you a little bit about why I'm in this webinar, and it's not because I'm a big researcher at the University of Maryland. It's because I'm working at Maryland as a result of a contract with DARPA. My background has been pretty much entirely in Silicon Valley, beginning at Fairchild and semiconductor test in the early 80s, and moving on to fault-tolerant computing in the mid 80s. And then I was recruited by Synopsys in the mid 90s to help them get their semiconductor IP program going. And I moved on to start my own company called IP Extreme in 2004, which I sold to Savaco in 2018. And then in the late 2018, DARPA came knocking on my door, asking if I'd be interested in helping them be a subject matter expert to help them on semiconductor issues around security of semiconductors itself. So that's what I do today. And I want to talk to you guys today about some things we're working on at DARPA around semiconductor security, including these supply chain issues that we've been talking about today. Next slide. So this is what we call our quad slide, describing the attack surface that we're worried about with regard to semiconductor security. And there's four of these that we kind of categorize the types of attacks that can happen to our silicon. The first one is called side channel, and this is formerly known as extracting secrets through a physical communication some way other than what's expected. So we're basically listening into a device either through power connections, through EMI, but attackers are trying to ascertain what's going on in the chip through these surreptitious methods. And for the purpose of the DARPA program is we're making some assumptions about all these attack things. So for side channel, we're assuming that the attackers have some vehicle to listen to the admissions that are coming off the devices. The next one is called reverse engineering, and this is where attackers are actually trying to steal your intellectual property, trying to understand how things are working so that they might be able to create competitive parts, stealing your trade secrets. And here we're assuming that the attackers have access to your design files. And I'll explain why that's a real possibility as we go through the next slides. On the third one here is malicious hardware. This is where an attacker will insert something into your design that shows up in your chip that the attacker can trigger at a later point in time to cause either damage or perhaps expose the side channel to steal particular information that they're choosing. And our assumption here for our DARPA program is that attackers have inserted a Trojan. And finally, and really the most cogent for the discussion today, is supply chain. And this is where cloning, counterfeiting, recycling, remarking chips improperly is a big threat. And our assumption here is that we're assuming that attacker can manufacture a perfect clone of the device that they're trying to sell you illegally. Now the background a little bit, I thought about this because when I first started with DARPA, I was really surprised that this stuff really happens in the wild, and I always wondered, well, why would people do this? And there's actually 3 reasons for this. The first is economic gain, which is I think the one we're talking about mostly today. But there's the other 2 are espionage. It can be conducted by a nation state or even sabotage. So those are the 3 kind of motivations behind why people would want to actually attack your silicon. So next slide, please. And I think we have a poll question come up here I'd like you to get your input on. And the question is, has a traceability or root cause analysis of one of your failures ever pointed to a counterfeit device or a clone device? I'd like to see what the audience's experience has been in this area. Okay, we're getting the results. Okay, so we have not a lot of you associated with this particular task, but a few of you have indicated that this is something, and I anticipate that this is going to be an increasingly bigger part of the future world we live in. So let's go to the next slide. And it's a little build coming here. So I just wanted to give a brief overview of this DARPA ACE program. AISS stands for Automatic Implementation of Secure Silicon. And the motivation for this program was the following problem statement, is that the threats the industry is seeing are increasing, and especially with IoT, this increases the surface area because all these devices are increasingly connected to the internet, which meaning bad actors can get involved and actually hack into your chips. This solar wind hack, the big hack that's in the news now, this is an example of an attack that's designed to leak information from these servers that were infected by this Trojan. So IoT is a big attack surface. The other thing is there's very few security experts in semiconductor. So if you're a big company, you probably can afford to have a team that can do that. But you're going to have to add things to your design to make them more secure. And just not every company can do that so easily. So what we're trying to do is make this a lot easier by coming up with a solution where we embed the security expertise into the design flows with new EDA tools and new IP that is security aware. And the benefit of that is for end users that are designing chips, we can give them kind of an option to add security as one of the constraints in their design. So typically engineers are worried about power, area, and timing when they're designing chips. We're adding a 4th constraint here called security that can be used, that the users can dial up how much security they want in their design and what types of security they really focused on. They're focused on side channel information leakage, or they're focused on supply chain, which is where this traceability stuff really comes into play. So next slide, please. So this is a kind of shows the entire semiconductor supply chain with all these different companies and data flow throughout the supply chain, starting at the fabless semiconductor coming from the design and going through mass preparation through foundries, through assembly and test into distribution, building, putting them on boards, putting them in systems, and shipping them all around the world. So every one of these red arrows in this diagram represents an attack surface where the design can be interrupted or the device can be interrupted, and bad parts can get infected and put into the supply chain. I think you'll get access to the slides eventually. There's a great little presentation from Andrew Wang, the Blue Hat 2019 Security Conference, that talks about in detail about the attacks that can happen at each of these places. It's definitely worthwhile having a look at that. Now, how this ties back to what we're talking about today is the next slide, which basically shows what we're doing on this DARPA program that also ties into the work that is going on in semi with the single device tracking that Dave and I are involved with, trying to establish a new standard around that. This particular example here shows blockchain being used for implementation of this. So you can see each of these little green smart contracts as devices flow through the supply chain. Bits of information are added about where the device was, where it came from, and that's tracked all the way through from enrolling device as it comes out of the foundry, all the way to the end of life when it's targeted for scrap. You'll see the at the top there we had this gray market guy selling hot dogs and chips on the market, and you'll see there's a kind of he's crossed out of this, and the reason this is because there's with this smart contract flow through a blockchain, there's no way for a device to get back into the supply chain unless it's went through the proper process. So if a foundry, for instance, would overproduce a device and somehow those wafers would get into the gray market, since they were never enrolled, they really can't participate in that supply chain. And the other example is if a defective part came back from a return, it'd be marked as scrapped and couldn't come back into the supply chain because it had been through a scrap stage of its life cycle. And that would prohibit that device from coming back into the supply chain. And I think that's my last slide. I think we're going to open up for questions. Let me summarize here. So we have a lot of issues on security that's increasing, and securing a supply chain is just one part of the overall secure solution. And I think it dovetails quite nicely with the traceability stuff that David talked about earlier. And these device tracking and smart contracts is at the early stages of things, but this is going to be really helpful in being able to track things into the future. And the benefits of having such a system is hugely important going forward for the kind of economic vitality of kind of all of us in working in semiconductor. Thank you.
All right, thank you so much, and great presentation there. So we're going to go ahead and, first I want to thank you, Warren. We're going to go ahead and start answering some questions that were submitted during today's presentation. So also remember, as a reminder, you can still submit questions through the questions pane on your control panel. So we're going to go ahead and start with Dave with our first question. This one is from Helen, and Helen asked how to read ID on package during final test. If you can answer that question for us.
Yes, I mean, first of all, yes, there's probably a 2D code marked on the package itself. That means it implies that you would have to read that package ID in the test handler that is feeding the devices into the tester. And that when you read that device ID, that value should be inserted into the test data log, which is uploaded to the traceability system, such as Exensio, and that would link that package ID to the test results for that package. And then the package ID itself links back to the strip and the assembly and everything else that we talked about. So yeah, you need an ID reader. That's part of the investment you're making in deploying single device tracking. You need to have ID reader, and you need a laser marker, of course, to mark it in the first place.
All right.
I hope that answers the question.
Yeah, no, thank you. So we are now at the top of the hour. So we're going to go ahead and, on behalf of PDF Solutions and our guest speakers from Cisco and the University of Maryland, thank you for joining us today. I want you all to have a great rest of your day. And just remember, once you leave today's webinar, there will be a survey on the presentation. We appreciate if you complete that and provide your feedback. And also as a reminder, there will be that follow-up email within 48 hours with a link to view today's recording. All right, thank you, everyone.
Thank you.
Thank you.
Thank you very much.